Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the second lecture. In this lecture, we'll be continuing with the basic concepts of integrated circuit. In this lecture, we'll be covering the types of integrated circuits, design styles, economics, and what are figures of merit for an integrated circuit. First, let us look into what is a VLSI design flow, right? Very top level understanding of what is a VLSI design flow. So, VLSI design flow is a methodology to design an IC such that it delivers the required functionality or behavior, right? So, it is a methodology of designing an IC, right? And the goal is to get the required behavior from the IC, right? Now, on what factors does a VLSI design flow depend on, right? So, what decides the VLSI design flow? So, the VLSI design flow depends on the type of integrated circuit, right? And what are various types of integrated circuit? We can divide or categorize integrated circuit either on the scope of application or design styles. So, let us first look into that what are the various types of integrated circuit based on the scope of application. So, there are two types of integrated circuit based on the scope. The first one is application specific integrated circuits or ASICs, and the second is general purpose integrated circuit. Let us understand the differences between these two types of integrated circuit. In terms of functionality, an ASIC or application specific integrated circuit is targeted to perform a specific task or the particular end system, right? For a particular end system. It is designed for a particular application. That is why it is known as application specific integrated circuit. While general purpose integrated circuits are designed to perform a wide range of integrated circuit. So, let us look at an example, then it will become very clear. So, an example of integrated circuit, an example of application specific integrated circuit is a digital camera or a integrated circuit for digital camera or integrated circuit for audio video processing or security chips. Here the application is very well defined, right? So, the chip, for example, digital camera is used just for digital camera, right? While a few examples of general purpose integrated circuits are microprocessors, right? So, we know there are many types of microprocessors and we can use microprocessors for many different applications, right? And similarly memory can also be used for many applications or FPGA chip, right? Then if using an FPGA we can realize many different functions or functionality, right? So, microprocessors, memories and FPGAs are examples of general purpose integrated circuits. Regarding programmability, what the ASICs or application specific integrated circuits are not that much programmable. Why? Because they are not targeted for those kind of applications, right? Because they are not targeted for general use. They are targeted for very specific purpose and therefore the programmability will cater to that particular purpose only, right? While general purpose integrated circuits such as microprocessors, those are highly programmable. Even FPGA, those can be programmed. Based on program you can get different functionality out of it. So, they are general purpose integrated circuits are usually software programmable and to perform a wide variety of different tasks. And regarding the volume of production, application specific integrated circuits, their volume is less. Why? Because they are targeted for particular application and those targeted application may not be or the requirement for those application may not be of a high volume product or so on. While for general purpose integrated circuits like microprocessor, FPGA, those are in general in nature, and there are wide applications of those chips, and therefore they will be catering to a larger, bigger market, and therefore the volume of production for general purpose integrated circuits will be typically more than for ASICs. Now let us look into that what are various types of design styles. So based on the types of design styles, we can categorize integrated circuit into full custom design, standard cell based design, gate array based design, or FPGA based design. FPGA is short form for field programmable gate array. Now we will be looking into each of these 4 types in more detail. Now what is a full custom design? In full custom design, what we do is that we design the circuit at the transistor level, at the lowest level, right? And we decide that the layout of the transistors, the geometric aspect like W by L of the transistors, and how those transistors are connected and so on, right? So the layout of the transistors and the interconnections, both all are design specific. We are designing at the transistor level in full custom design, and as a result, since we are designing at a very low level, we need to make a lot of decisions manually, and therefore huge design effort will be required in full custom design. And there are only a few designs which are full custom, right? A few example of full custom designs would be, say, analog circuit design or mixed signal designs, where the design produced by manually designing at the transistor level typically achieves a better results or better performance and other measures for analog circuits compared to the automated flow, right? For in those cases, the full custom design is done, or the case in which there is a high volume product, for example, a microprocessor, which is a very critical product, and in that microprocessor there are some critical path, and in those paths we will be trying to design at that probably transistor level, because we want to improve the performance of that particular path to a much higher level, and therefore in the full custom design may be undertaken for those particular paths in microprocessors or high volume product, right? So but in general, full custom design are less done than other types of design styles. And what are the merit of full custom design? The merit is, of course, the optimization, right? We are designing at the transistor level, therefore as a designer we have a lot of flexibility for a full custom design, and if we have that flexibility, we can utilize it to improve the quality of our design, and as such the quality of full custom design can be much better than other types of design styles. The other design style is standard cell based. Other design style is standard cell based design. So in standard cell based design, what is done is that first we design standard cells. Now what are standard cells? Standard cells are simple cells such as AND gate, OR gate, or flip-flops, or simple adders and those kind of things, right? So these are gates, logic gates, or simple cells. It can be macros also, complex cells such as full adder, multiplier, memories also. But what we do is that we first design at a transistor level these small cells, AND gate, OR gate, and other standard cells, and characterize that and put that information in a kind of library. Once we have designed those AND gate, OR gate, and those kind of standard cells, we do not touch the transistor. We treat the complete standard cell as a unit and use that in our design. So there are two levels of designing done in standard cell based design. First, the designing of the standard cell per se, which is done at the standard at the transistor level, and we do it very optimally. We design each of the cell and then put all that information in a kind of library, and in the next step what we took is that use those standard cells which are in the library in our design. And that is what the freedom in this case for a designer who is not doing the standard cell design or general design, so who is doing a general design using standard cell design. In that case, the level of freedom is only which standard cell to use and how to connect them, right, and how to put them on the layout. The internal details of standard cell are not allowed to be changed by the designer who is making a design, right. So when we make these standard shells, we typically keep the height of the standard shell as fixed, right, and as such the properties of these standard shells are well defined in terms of geometry and other things, and therefore it allows a high degree of automation. For example, we can put the standard shell in a row kind of thing. Why we can put it in a kind of row? Because the height of all the standard shells are the same, and therefore we can put all of them in one row and then make the connections, right. So these are standard shells, right, these are standard shells. And in a standard cell design we can also use macros which are bigger shells, maybe multiplier, memories and other things, and we can also have IO patch, right. Now rows of standard shells are used in standard cell based design with interconnections between them, and custom blocks can also be embedded. The types, location and interconnections of standard shells are design specific. So since we are allowed to change the location of standard shell, and standard shell internally contains the transistor, what it means is that when we make a design, all the layers, even the device, the mask related to the device layer and also for interconnect layers, those will be design specific. Why? Because we don't know where the devices are on the layout. That the layout is still made by the designer. What, right? Why? Because where to place exactly the standard shell, that freedom is still with the designer. We are not changing the location of a transistor within the standard shell, but one standard shell can be placed over the layout anywhere as per the wish of the designer. Okay. The third type of design style is gate array based design. So in gate array based design, what happens is that the transistors are predefined on an IC in a form of a gate array. So the transistors are there or predefined. So designer has no control that where the transistor will be on the layout. That is predefined. And these transistors, or in a gate array based design, there is the smallest element that is repeated to form a gate array, that is known as base cell or primitive cells. So these base cell or primitive cells are pre-placed on the layout, right. What the designer can change, the interconnections between the transistors. So since the devices are already at a fixed location, therefore device layer will not change, but the designer can change the metal layers over, or how the connections are made between the primitive cells. Therefore the top layers, upper layers of the gate array based design, those are design specific, right. So for gate array based design, realizing some functionality, for example memory, can be very difficult, right. Why? Because we have only a primitive cell and we have to design everything in terms of primitive cells. However, the vendor of gate array based design, they may allow to they may have products in which these memories, microcontrollers, etc. are pre-embedded in your layout in the gate array based design, and those can be reused for obtaining the functionality. The fourth design style is FPGA based design. Now, In FPGA based design, what happens is that the hardware is totally fixed. The designer do not have any control over the hardware, meaning the hardware, the structure that is there, it is already there, right? What the designer can do is that they can program the connections between the hardware, right? So designer obtain the desired functionality by programming, and by programming what is done is that the programming basically makes changes in the interconnections between the elements of the circuits. So what are elements of circuit inside an FPGA board? So FPGA consists of array of logic blocks. For example, these are logic blocks, right? And there will be IO blocks which are at the periphery through which the signal can enter and leave. And there can be routing channels which are basically used for making connections between different logic blocks. So logic blocks can be programmed to perform different functions such as AND, OR, adder. So the functionality of each of the logic blocks can be changed as per requirement, and also their interconnections. But understand that the hardware is fixed. Once we get a hardware from a FPGA vendor, hardware cannot be changed. But the connections, internal connections within the hardware, that can be programmed, and the vendor typically gives some tools to program those hardware through high level languages. So FPGA boards may also have embedded microprocessors, analog components, and blocks for performing special functions such as DSP block. And the most popular are Xilinx or AMD FPGA boards, and Altera or Intel boards, which are used typically in the semiconductor industry. Now, just to summarize that what are differences in the design styles, why we should understand its design styles carefully, because our design flow depends on which design style it is, right? So in this course, we'll be typically looking into the standard cell based design, right? This is our area in which this course is working, though the concepts that we'll be using will be applicable at least partially for FPGA based designs, and a lot of them will also be valid for custom based design. Just to summarize the differences between these 4 design styles. So the full custom design is a design style in which the customization is done at the level of transistors and layout. In the standard cell based design, customization is done at the level of interconnections between standard cells, right? And also the instances that will be used inside our design, that is customized by the designer. In gate array based design, only the top level connections are design specific. The transistor is all predefined, and in FPGA board the complete hardware is predefined. We can only change by programming, we can change the connections, and also the logic blocks the functionality of individual logic blocks can be changed. Now in terms of design effort, the full custom design has the highest effort, it requires highest effort. Standard cell based design will also require a high effort, but less than full custom design. And in gate array based design and FPGA based design, those have lower design, those require lower design effort. And then there are the mask layers in full custom design. All the layers, the device layers and interconnect layers, both for all of them the mask layers will be custom or design specific. For standard cell also, for the device level also, and for the interconnection also, the mask will be design specific. For gate array based design, only the top level mask will be design specific. The bottom layer will be, or device layer, is predefined. There is no control of the designer over them. And in FPGA, the hardware is given by the vendor, and the designer do not have a control over the hardware as such. Then in terms of power, performance, power and area, that is the quality of the design that we get. The full custom design of course has the best. Why? Because we are designing at the transistor level, we have the full flexibility to make our own design, and therefore full custom design can achieve the best performance, power and area measures. The standard cell-based design also are very good in terms of power, performance and area, right? And comparatively, the gate array based design and FPGA based design are inferior in terms of quality. But the strong point about FPGA based design is that the design effort is less, and if there are any bugs, it can be easily fixed in FPGA based design by reprogramming. Now, there are different design styles. When we start a project, how do we choose which design style we need to use in our project, right? Whether we should use an FPGA or whether we should use a full custom, or whether we should use, say, a standard shell based design, right? A lot of this decision, or one of the major factors that decide these decisions is the economics of the integrated circuit. So what we mean by economics of integrated circuit, let's understand that. So if we consider the cost of an integrated circuit, there are various components, and we can divide into two types. The first one is fixed cost and the other is the variable cost. So fixed cost are those cost components which do not depend on the volume of product, right? Meaning that if we produce, say, 10 items or 1 million atoms, the cost will remain the same. Those costs are known as fixed cost. For example, the cost of designing a circuit, right? The designing is done only once, right? It will be manufactured many times, right? But the designing will be done once. Therefore, the design effort is a fixed cost. Either we produce, say, 100 chips, or we make 1 million chips. The design effort will be the same, right? And that's why it is a fixed cost, right? And then there are costs related to software tools that we use in designing. Again, that will be that those are one-time cost, right? And the hardware that we require for designing, for example, CPU, the computers that we use to make the designs and those things, those are fixed cost. It doesn't depend on the volume of product or the chip that we manufacture. And the cost of the mask, right? So the mask is also made once, and the same mask is used multiple times, right? And that is why that makes the copying of integrated circuit much easier, because mask is prepared once at a very high level of accuracy, and that mask is replicated on the integrated circuit. But so the cost of developing that mask is a fixed cost. It doesn't depend on the volume, whether we make 100 chips or 1 million chips. The mask will still be fabricated, and the cost of the mask will depend on the number of layers, right? And then there are variable product costs. For example, cost of the wafer. Now, when we take a wafer and make a circuit on the wafer, silicon wafer, we need to use chemicals, for example, for photolithography and other stuff. Now, those chemicals will be dependent on the volume. If we are making lots of products, then more chemicals will be required, and therefore that is a variable cost depending on the volume of manufacture. And the cost of the die, the area depends on the area or the size of the die. If you have a small die, then on a given wafer you can have many those small chips, right? But if you have a larger one, right, then larger area, then on the same wafer you will have less number of dies on that wafer, right? And therefore the size of the die will impact the cost of the die, and that is a variable cost. Depending on the volume of die produced or the chip produced, you will incur more cost, right, or less cost. And then the yield means that out of, say, 100 chips that we manufacture, how many are defect free, right? So manufacturing is a complicated process, and when we manufacture a chip, all of them cannot be defect free. Typically, if it is more than 95% of the chips are defect free, we say that the yield is good, right? So yield defines that out of all the manufactured chips, how much percentage is basically good, right? So the variable cost will depend on the yield. If the yield is high, variable cost will come down. So these are major divisions of fixed cost, or the major divisions of cost for an integrated circuit, right? So we can write that the total product cost depend on the fixed product cost plus variable product cost into number of products, right? So as the number of products increases, the variable cost, product cost per piece remains the same, but number of products that will increasing. So this part will increase and your fixed cost will remain the same, right? So now let us compare for two types of design styles. Let's compare standard cell based design and FPGA based design and compare their fixed cost and variable cost. Now for standard cell based design, the fixed cost is high. Why? Because it requires more design effort. It requires more costly tool for designing, EDA tools and other things. It will require all the mask customized for a design and so on. So the fixed cost will be higher for standard cell based design, but it will be lower for FPGA based design. Why? Because to get a design we need to just do the programming, and therefore the design effort will be low, and therefore the fixed cost will be lower. And what about the variable cost? Now for standard cell based design, the variable cost can be lower. Why? Variable cost per unit product will be lower. Why it can be lower? Because the cost of the die will be lower, because we can optimize our design to occupy less area on and die area can be reduced, and as such you can get more dies on a given wafer, and therefore the cost can be, the variable cost can be made down, right? And for FPGA based design, typically if we get a hardware, the vendor, and we do not utilize the complete hardware, right, for our functionality, and therefore the cost of the die will be higher for FPGA based design, because the area will be larger for FPGA based design, and because of the larger area, as we will see later, that the yield will also be lower, and in effect what happens is that the variable cost of FPGA based design will be higher compared to the standard cell based design. Now to just give you a very crude estimate of like what could be the cost looking like for the FPGA based design technology and standard cell based technology. This is a very crude model in which we are assuming that standard the variable cost is linear function of number of units, right? So for the standard cell technology, the fixed cost will be higher, right, and compared to FPGA based technology, but it will be rising at a slower rate because the variable cost is lower for standard cell technology. For FPGA technology, the fixed cost will be lower, but it will be rising at a steeper rate compared to with the number of units compared to standard cell based technology, and therefore there will be a break even point. And below this break even point, in this region, the FPGA technology will have less cost for a given volume, and in the right region we'll have the total cost for a given number of units that will be lower for standard cell based technology. So what this analysis means is that typically for small volume FPGA is better, right, and for large volume standard cell based design would be better, right. So this is just for illustration purpose. So the cost versus number of units may not be a straight line as that is shown in this figure. This is just for the illustrative purpose. Now in addition to the economics, the another important part or another important factor that decide which design style to use is the figures of merit. figures of merit for an integrated circuit. Now, what do we mean by figures of merit? So, when we make an integrated circuit, the fundamental question is that how to measure the goodness of that integrated circuit, meaning that how good it is compared to some other design integrated circuit. So to measure or assess the goodness of the integrated circuit, we use some figures of merit, right? So figures of merit, and one of the or three important factors which are considered as important figures of merit are power, performance, and area. Together they are known as PPA, right? So what is power? Power is basically the sum of static and dynamic power consumed by an IC. So whenever there is an IC, that IC can be doing active computation. So the power consumed by that IC when it is doing an active computation, that is known as dynamic power, right? And the power that is consumed when the IC is not performing doing active computation, that is known as static power dissipation. So these two numbers basically define the power numbers for an integrated circuit. The other figure of merit is the performance, meaning that how fast your chip is working. So typically it is measured by the maximum frequency of clock at which an IC can work, right? For example, if the IC is working at a higher clock frequency, then we say that it can give more, it is operating faster, right? And the third figure of merit is the area of the die for an IC, because that determines our variable cost that we have just seen, right? So typically for a chip, we'll say that for this particular integrated circuit, these are the PPA numbers. For example, we can quote that 1 watt, 2 gigahertz. So this is the power number, this is the performance number, and this is the 1 millimeter square is a area number. So typically when we design an integrated circuit, we quote the PPA for that integrated circuit or figures of merit. Now, in addition to PPA measures, there are other figures of merit. What are other figures of merit? Those are testability, so reliability, and schedule. So what do we mean by testability? Testability means that how good we can test an integrated circuit. As we discussed that when we manufacture an integrated circuit or fabricate an integrated circuit, all are not defect free. Some will be having defect, some may, and most of them will be defect free, right? But we want that only the good product or the integrated circuit without any defect, those actually reach the customer, right? So we want that the chip in the integrated circuit that we manufacture, that is tested. Before shipping it to the customer, we want to test it and then only give it to the customer, so that our customer do not get any faulty product, right? So that how good we can measure or test the product after manufacturing, that is known as testability. Now, some integrated circuit may be very good testable, meaning that if it is defective, we can know that it is having defect. And some integrated circuit may not be that easy to test. Then the testability of that product will be lower, and probably bad integrated circuit for that particular badly manufactured integrated circuit, for that case can reach to the customer and can be troublesome for the reputation of the company, right? The other figure of merit is the reliability, meaning that how does the performance of a chip, or how does the quality of a chip or an integrated circuit deviate from the rated behavior with time, right? We want that with aging, the performance of our chip should not degrade below the acceptable limits for at least the rated age of the chip, right? So that measure is the reliability, right? Another figure of merit or schedule is very, very important, right? So schedule means that how much time have we taken to make a design, right? Or this is also related to time to market. We given a specification, how much time did we take to design that chip? Typically, the success or failure of a product highly depends on the schedule. If we can design a product very quickly, right, or design an integrated circuit very quickly, we can bring it to the market quickly and as such capture the market share and so on. Therefore, the schedule or the time spent in design, that is very important and is one of the important figures of merit for an integrated circuit. And these figures of merit are also known as quality of result, especially when these results are obtained using EDA tools and we get a measure of the performance, power, area and other metrics, then we call it these figures of merit as quality of results. And an important characteristics of these figures of merit or quality of result is that when we improve one of these characteristics, the other characteristics, other measure can come down. For example, take a circuit in which we want to improve the speed of the circuit, right? Probably we can improve the speed of the circuit by using a bigger transistor, or the transistor which is driving the load very quickly, and use a wider transistor and so on. But as a result of improving the performance or speed, what has happened is that we are increasing the area of our design, right? And therefore, when we improve the performance, the area also goes up, and which is a bad thing. And typically, when we improve the performance, the power number also can go up, right? So when we improve one matrix, the other matrix can actually come down. And therefore, designing is always a step or a process in which we have to choose a trade-off, right? So we have to always trade off some measures to improve some other, right? So when we design, we need to understand these aspects very carefully, that when we are improving it, what other things is becoming bad, and whether that becoming bad is acceptable or not. And the problem becomes more complicated because there is a dependency of these figures of merit on the design parameters is very, very complicated. And it is typically finding a mathematical optimum for these figures of merit is rarely known, or forget about achieved, right? And that's why the goal of a design flow is not to go for an optimum solution, because that we most of the time do not know what is the mathematical optimum. The goal of design flow is to find one of the feasible solution with acceptable figures of merit, right? So we do a designing such that we get a feasible solution and the figure of merits are acceptable as per our requirement. So this is the design goal. And in the next lecture, we will be looking into how we can achieve these design goals in a design flow, or what is the role of design flow in achieving this figure of merit in some better or optimal way, right? So this brings us to the end of this lecture. These are some of the important references that I have used in this lecture. Thank you very much.